you actually use like opposite over adjacent or that kind of thing. And then cotangent, the reciprocal identity, and it is also the reciprocal of tangent, so cosine over sine. But you could also do that in a couple of steps, which you probably don't know what I mean by that yet, but you will. And then these are called the Pythagorean identities. So sine squared theta plus cosine squared theta equals 1. If you, that comes from like angles in standard position when you look at that triangle, or any triangle that has a hypotenuse of 1, you could demonstrate those. Little piece on notation. What does sine squared theta mean? A lot of people are terrified of identities. They're probably like just in shock that this is starting already. Like, oh my gosh, we're doing identities. I can't believe this. Yeah, it means sine theta times itself. Exactly. So it's a different way of writing sine theta all squared. Okay, so that is the notation that we use. Sine squared theta. Okay, and there's a couple other different versions of that. 1 plus tan squared theta is secant squared theta, and cotangent squared theta plus 1 equals cosecant squared theta. Don't see those quite as much in a lot of ways, I would say, but they do come up here and there. And here's my list of strategies to get started. And I know that this can be difficult at first, so honestly, I would have this list of strategies written on a little piece of paper and have it beside me while I'm working and be like going down the list looking for all the possible things you could try, because they might not jump out at you until you've done it a few times. Now, we're doing a little bit of practice with some grade 11 identities right now, but then for the next few days, we're actually not doing identities. So we're going to do other things similar to identities, but some other skill-related stuff, and come back to identities maybe by the end of this week or early next week kind of thing. But we'll have a whole bunch more identities to use by then. So we're going to do a handful together today, and there's going to be some practice, and I have an extra handout that I'm going to post to the classroom that I would say maybe is optional, but if you want to be prepared for when the grade 12 identities start, I would suggest trying at least some of them. Like over the course of the week, trying one a day or something like that. And again, using this list of strategies and go down the list. Well, could I do this in this case? Could I do this? Could I do this? Because then by the time we get to identities that we're going to do in this unit, in this course, you'll have a little bit of practice, you'll be a little bit warmed up. And when you see an identity, you won't just go, I have no idea where to start. I have no clue what in the world to do in this case. You'll be like, oh, maybe I could try this or maybe I could try that. Okay, so here's my strategies. These are just standard kind of things. Work independently on each side. That's less of a strategy, that's more of a sort of rule. This is like when you're doing a left side, right side check, which some people don't do properly as a left side and right side separately. And then they start like multiplying both sides by something. You can't do that with identities. You don't multiply both sides by tan and multiply both sides by 1 over cosine or something to get rid of all, like you can't do that. So we work on each side independently. We'll see that when we get down there. Change everything to sine and cosine. So if you see tangents or cotangents or secants or cosecants, not always, Like there's no rule. This is the problem. Is there's no rule that every single time you do this first, then this first, then this first, and you'll be done. That's the problem. That's why people find this hard. But it's a good idea to change things into sine and cosine. We're more familiar with those identities, the Pythagorean identities and those things, and it tends to help things work out. So if everything is in, for example, tangent and secant, well, then maybe I can change stuff to use that, right? If the whole thing only has some tangent squares and some secant squares, then maybe I don't need to change things. Maybe it's like leaning towards using this identity, right? But normally, if you see any kind of mix of stuff, or if you see one sine or one cosine, switch everything else as much as you can to sine and cosine. Start with the more complicated side. That's usually a good idea, and some of these strategies will help simplify it. And then once both sides are the same level of complexity, then you probably can kind of see where to go from there. Look for common denominators, or get common denominators and add fractions. That's part of simplifying. So simplify where useful, and sometimes we're going to expand when it's useful. But this is tricky because it also says here factor when possible, and those are opposites. So like if you factor and then expand and then factor and then expand, you just got to go back and forth. So it is part of looking a few steps ahead, like a game of chess, a few steps ahead. Well, if I do this, what will happen? If I do this, what will happen? Right? So often factoring is a good idea. If it's factorable, that's probably kind of like designed on purpose by the question. It's harder to see these factors, at least at first, but we're going to see a couple today, so that should help. But sometimes you might want to expand and simplify instead. Okay, look for common denominators or put things in common. If you have fractions, put things in common denominators, or if you're multiplying fractions or dividing fractions, multiply by the reciprocal. That often helps. And whenever you see squares, think about Pythagorean identities. There's a lot of ways that we can use the Pythagorean identities, even just this simple one. Because this simple Pythagorean identity can also be written as sine squared theta equals 1 minus cos squared theta, or cos squared theta equals 1 minus sine squared theta. And those guys come up a lot. It's not always in its main form. And then obviously same with the other ones. I can move terms around. Tan squared theta is equal to secant squared theta minus 1. Right? Any questions so far? I mentioned this the other day, QED. So that's what it stands for. You don't need to write it down, but if you're curious, that which was to be demonstrated. So it's a nice way of finishing up your proof, saying, I'm done. All right, let's take a look at our first one. Super easy. So here's how we start. Left side equals tan squared theta cos squared theta plus cos squared theta. And then right side equals 1. That's what we mean by split up. Work on them independently. Very rarely, and by that I mean probably never, would you take a right side equal to 1 and turn it into something and start doing stuff. Like turn it into sine squared plus cosine squared and start trying to do things, because you have no idea where to go with that. Like should it be sine squared theta plus cosine squared theta, or should it be sine theta over sine theta? That's also 1. Or tan theta times cotangent theta. That's 1. If you're not sure about that, you can think about it. Like what would you turn that into? So this is what we mean. Like we got to start with the more complicated side and start simplifying it. It doesn't get more obvious than this. Which side's more complicated? The right side is 1. You're probably not going to touch it. So your job here is to take the left side and turn it into 1. And so look at the list of strategies. What are a couple of things that you could try here? There's no fractions, so we're not talking about common denominators. What do you see? What do you notice? What's relevant about this question? Very good. So we've got a bunch of cosines and a tangent. So why don't we change tangent into sines and cosines? That would be one very good strategy. In fact, that's what we're going to do. But even if it wasn't, that would be like a good idea. Like in this case, you pretty much always would. I can't think of a time where you wouldn't. Okay, so that's what we mean by change everything to sine and cosine. You see tan squared theta, change it to sine and cosine. What else do you see? Not relevant yet, but I see a whole bunch of squared stuff. So I'm thinking about the Pythagorean identities. Like this is something plus cosine squared theta equals 1. That's close to that other identity. But I'm not there yet. I don't know the answer. I don't know what's coming. I'm just thinking there's a lot of squareds in here. And there's a 1. That's a lot like that main Pythagorean identity. So how would I change tan squared theta to sine squared and cosine squared? How would I do that? Like, what does it look like? Like, do it if you think you can do it. Brandon? Right, so sine squared theta over cosine squared theta plus cosine squared theta. Times cosine, missed the times. Thank you. Times cosine squared theta, there we go, plus cosine squared theta. Right? And now what do you see? Like now, that easy, you probably kind of see the result, see the end. Which is? Brilliant. So those divide to 1. Sine squared, see how easy this is? Cosine squared theta, which equals 1, which equals the right side, QED. You have to finish what, you can't just stop with, you have to say, you don't have to say QED. You can say therefore proven or therefore true, or what, you can say whatever you want, but you have to say equals right side, therefore true. QED, whatever you want to say. Easy enough, right? Okay, let's try this one. So left side equals secant squared theta over 1 plus tan squared theta, and right side equals 1. There's a really easy way to solve this one. 1 plus tan is secant. That's one of our identities, and then it's just solved. But I'm going to do it a long way to show a couple of tricks and strategies that you can use. Okay, so we're going to do this one a long way. It also kind of proves this identity, that secant squared theta is equal to 1 plus tan squared theta when we go through these steps. Okay, so we're going to do this the long way. However, thank you. Oh, and this brings up, this probably won't make a lot of sense right now, but down the road, like every time you prove an identity, that kind of makes it a new identity. Like it's something that's just always true. That's what an identity is. An equation like 2x equals 10 is only true when x equals 5. That's what it means to solve an equation. You're finding when it's true. In grade 9, you only have one x value that is true. In grade 10, you get 2x values where it's true because you do quadratics. We've done all kinds of stuff, right? We've done up to degree 4, degree 5 that can have up to 5 solutions, and all kinds of other stuff where they have multiple solutions, right? So we've seen equations where you find the value of x that makes it true, and there's lots of solutions. And then periodic functions, you do this in grade 11, like these, when you're solving trig equations, are true like over and over and over again, possibly at least, because they're periodic, so they keep meeting over and over and over, right? Anyway, what is an identity? How is it different from that? Identities are always true. In other words, it doesn't matter what value of theta I put in here, it will always equal 1. That's what an identity is. It's true for all values of the variable or both. We don't do multiple variable stuff really, but well, we might actually, but not yet, right? So for all values of the variable, it's true. That's what an identity is. So if you prove an identity, it kind of becomes an identity. But that doesn't mean you're allowed to use it. This is my point. You're not allowed to just say, oh, I proved something like this that was slightly different, so I'm just going to like skip those 10 steps and say this is true. No. Like it's got to be the ones that are set in class. So far, it's just the reciprocal and Pythagorean identities. Those are the only ones we're actually allowed to use. That being said, one of them would work to solve this immediately, but we're not going to do that because we're going to demonstrate some more interesting skills. So what we're going to do is change everything to sine cosine. Okay, so let's do that. So what is secant squared theta? 1 over cosine squared theta, good, over 1 plus, what's tangent squared theta? Some people say, well, it's 1 over cotangent squared theta. That's not going to help us. Like cotangent gives us nothing, right? We're trying to change everything to sine and cosine. So how would I write tangent squared theta in terms of sine and cosine? Sine squared theta over cosine squared theta. I'm going to start picking on people. I don't like the quiet because I have no idea if you're like lost and you can't see it or if it's just obvious and you don't want to answer. Like if you don't see it, then we can keep talking about it. But if it's easy and if it's obvious what tan squared theta is, then great, we'll move on, right? So those are two very different things. So I want to like see eyes or hands or something that people are seeing this. So that didn't give us much. What's one of the other? Like I've got a big mess here. So this is, to me, this is a great place to be stuck in with an identity. It shows us a lot about strategies. I've got a fraction on top. I've got a fraction on bottom, but it's also a sum. Like it's a bit of a disaster. I can't add anything. I can't multiply. I can't like multiply by the reciprocal here because I've got a sum in the bottom. So what would you do? So this is a difficult trick. Here's a really good idea. I'm going to take that one. I don't touch a 1 that's all by itself on a side, but a 1 in the middle of a bunch of junk. Watch. Cos squared theta over cos squared theta plus sine squared theta over cos squared theta. Common denominator. That's what we're talking about. See how I just used 1? I can turn 1 into so many things. Turn it into almost anything I want it to be, right? So I turn it into cos squared theta over cos squared theta. Common denominator with the thing it's supposed to be added to. I can guarantee you 90% of the time when we're looking at something like 1 plus a fraction, that's going to help. That being said, it is true. Sometimes you try something that's a good idea. It doesn't get you anywhere, and you got to erase it all or scratch it all out and go back. Like that does happen. Especially depending on how good you are at looking a few steps ahead, right? We all have our different strengths. Okay, so now I can do common denominator adding here. So 1 over cos. And if you can see a few steps ahead, you see how this is going to work out already. Over cos squared theta plus sine squared theta. What's that? Over cos squared theta. What's cos squared theta plus sine squared theta? Chad? 1. So I get 1 over cos squared theta over 1 over cos squared theta. And what is anything divided by itself? 1 equals 1 equals right side. Done. Look at all that cool stuff we would have lost if we had taken the shortcut. That being said, like, you're not supposed to do that when you're working. Can if you want, I guess, but. Any questions so far? How's everybody feeling? No, not really today, actually. Pretty easy. Cosecant squared theta plus secant squared theta is not a Pythagorean identity. That doesn't mean it's not true. It just means it's not a given that it's true, and we're not allowed to replace it with 1. So it's secant squared. It's supposed to be. You could try to prove it if you want. But if you think about what cosecant squared theta and secant squared theta are, they're reciprocals. I don't know that that would make sense that they always add to 1. You could try it if you want. Like, you could think about other reciprocals and see if they hold that pattern. But anyway, that's not how we're going to solve this one. Okay, so let's get this started. Left side equals. Whoops, cosecant squared theta times secant squared theta. Which side's more complicated? That's a bit debatable. Probably the side where you're adding in some ways is, but really I'm not sure if one or the other. So you know what we're going to try here is we're going to do a bit of work on both sides. And I don't see, there's no tangents in here or cotangents. So it's not looking like those other versions of the Pythagorean identities. So to me, it looks like, yes, there's a whole bunch of squared stuff, but we want to move everything to sine cosine. Okay, I think is what we want to do. So let's get started on that. So on this side, cosecant squared theta is 1 over sine squared. Secant squared theta is 1 over cosine squared. And on the right side, there's no reason why you can't do a step on each side. Like, that can happen. Absolutely. So this is, again, 1 over sine squared theta times 1 over cosine squared theta, which is just 1 over sine squared theta cosine squared theta. Just a different way of writing the same thing, right? Any ideas? What would you do? Very good. Let's try it. I'm going to show my work so that we can follow it and kind of everybody can make sure they understand exactly what's happening. So common denominator means I'm going to have a sine and a cosine on the bottom. So I'm going to multiply by cosine squared theta on the top and the bottom, plus 1 over cos squared theta. And then again, multiply this by sine squared theta over sine squared theta. So that is 1 times cos squared theta, which is cos squared theta, over sine squared theta cos squared theta, plus 1 times sine squared theta is sine squared over sine squared cosine squared. Common denominator, so I can add those. Cos squared plus sine squared. And what is that? Chad? 1. That's our Pythagorean identity. And there's done, right? That's our right side. Oops, why did I write that plus? Where did that come from? Times. Oops, Q, E, D. Another good demonstration of how common denominators, changing sine, cosine, really works things out. Your first step or your first couple of steps will make it look more complicated, but then things start simplifying. Once you get the common denominators, they tend to start simplifying. So, I mean, again, to some extent, you do have to be able to look a little bit, a couple steps ahead or 1 step ahead to see when I get a common denominator, what will the outcome look like? All right, couple more. Looks to me like we should start with the left side. This one's a bit trickier, so I'm going to go ahead and kind of go through the steps on this one, follow along. It's going to show another trick that sometimes you might have to make use of. A lot of these things, like the practice today, is pretty straightforward. I think quite simple. I don't think there's any real like big tricks, kind of like this, but gives you a sense of the kinds of things that can work. And so your job over the next couple weeks is to put yourself in a position where you recognize when to do these things and to remember them. So I would look at this and I would say, well, I've got a sine squared and then cosines. That's a tricky situation to be in. They're different powers. So, but there's something that I notice about the way that the cosines are all written, that once you get to the end, you look back and you go, okay, yeah, I see, now I can make that connection. So what I'm going to start with is on the left side, is turn this into 1 minus cosine squared theta over 1 minus cos theta. That is not 1. That's not something divided by itself. It's not even close because it's cosine squared theta and just cosine theta on the bottom. So, there's nothing much that I can do there. But here's an important trick to know. 1 minus cosine squared theta is a difference of squares. 1 is a perfect square, and cos squared theta is a perfect square. How do you factor a difference of squares? Bracket 1 plus not cos squared theta, cos theta, and 1 minus cos theta. And look at that. These divide to 1. And we're done. So if you're thinking to yourself, yeah, that's all well and good. That was nice and simple. That was great. That was really elegant. But how am I supposed to know how to do that? Well, that's what I'm talking about. Like over the next couple of weeks, you got to get used to trying to look. So that list that I gave you of strategies, add on your own. Make some notes to yourself about what you can do. Like difference of squares like that. See what I mean by factor where possible? How would you know to do that? You got to look ahead. You got to think, well, see, I can visualize. See, I know that sine squared theta is this, and I know when I break this up, I get something like 1 minus cos and 1 plus cos, right? The factors of that difference of square are on the bottom on this side and the top on that side. That's got to be worth something. Like, that's got to be a hint that when you do that, things are going to work out. Even if you don't know exactly how, it just looks to me, one of the factors is there and the other one's there, that's what I should be doing. That's the kind of thinking that you would look at. That's what happened. That's what I think about. I think, okay, so I know what sine squared theta is. I know how to rewrite that. Difference of squares, and those factors are staring right at me there. That's got to be the right step. Okay, so if you practice enough, you get to the point where you can see those things. Okay, I think this is the last one. It's always scary when there's a 2. We deal with a lot of 1s. Where does that 2 come from? So don't worry about the 2. It'll probably work itself out. What do you notice? What would be your strategy? Don't sit there and say to yourself, I'm going to wait for somebody else to answer this question. Think, what would you do? It might be right, it might be wrong. You don't even have to do it because we're going to do it together, but I want you to think about what you might do in this case. Or not even what you might do, but just what do you notice? Ross, what do you think?
Denominators, I like the differences there.
Very nice. Isn't that right? Good? What else? What else? What are the other strategies? Frank, what do you think? What would be your gut feeling? What you would do in this?
When you multiply the denominator, like combine them together.
On the left side, common denominator.
You get
Okay, hold on. Don't tell us what's going to happen. Very good. That's what you would try. Looks like it's going to be a bit messy at first, but if I get common denominator on the left side, because I've got one fraction on the right and 2 fractions on the left. How do we get 2 fractions into 1 fraction? Common denominator. At some point in this problem, that has to happen. If the left side is going to look like the right side, it can't be 2 fractions. It's got to be 1. How do you do that? Common denominator. So let's start with that. So that equals, so I'm going to multiply by 1 plus sine x on the top and bottom over here. So I get 1 times 1 plus sine x, right, in brackets if we really want, over 1 minus sine x, 1 plus sine x, plus 1 over 1 minus sine x, 1 minus sine x. All right? Okay, good. Okay, so this is where we start kind of simplifying. So I get 1 plus sine x plus 1 minus sine x over, and you don't have to do this in 2 steps, but we might as well, or in the same step, you could do it in 2 steps if you want. If you didn't see it, like it is hard to kind of be working on top and on the bottom unless you know where you're going. But we're going to expand the bottom, and the bottom is like the factored form of a difference of squares, right? 1 plus sine, 1 minus sine. See that? X plus 3, x minus 3, x squared minus 9, right? It's a binomial expansion. So it works out, I'll do that on the side after if you don't see it, but it works out to 1 minus sine squared x. What do we get on top? 1 plus 1 is 2. Yep, there's our 2. Sine x minus sine x. 0. Gone. Over. What is 1 minus sine squared x? That's a rearrangement of? Yeah, good. Of that Pythagorean identity. Cos squared x, which equals the right side. And we are done. Common denominator, and then things just fall into place. It doesn't always happen, but often that's how identities work. If you've got 3 pages of steps for one identity, you're probably on the wrong track. Usually it's only a few steps, sometimes a bit more. What was our biggest one here? 1, 2, 3, 4, 5, kind of. 1, 2, 3, 4, 5, 6, maybe. So yeah, that was the biggest one. Any questions? All right, just because I glossed over that, I want to make sure people understand. So when I had this 1 minus sine x, 1 plus sine x, I was saying it's kind of like this. I'll do 3 plus x, 3 minus x. It's been a long time since you've... I know this is probably obvious for most of you, or maybe everybody in here, but 3 times 3 is 9. 3 times negative x is negative 3x. X times 3 is plus 3x, right? They're gone. X times negative x is minus x squared. Those are gone, so it's 9 minus x squared. And it would be the same with 1 plus sine squared, sorry, sine x, not sine squared x. 1 minus sine x. 1 times 1 is 1. 1 times negative sine x is minus sine x. Sine x times 1 is plus sine x. So there's your, they add to 0, and then minus sine squared x. Sine x times negative sine x is sine squared x. Gone, and you get 1 minus sine squared x, right? Any questions?